Hello everyone and welcome to our Continual AI April seminar. So we have today two speakers, Monika and Mew. Monika is a recent PhD graduate in computer vision and machine learning in the Computer Vision Lab of Warsaw University of Technology. During her PhD, she collaborated with various labs, including the Valeo AI team in Paris and the imaging group of École de Ponts. She also interned at Google DeepMind and Booking.com. Her research revolves around vision foundation models and adapting them to different contexts and downstream tasks. And with that, I will give the camera over to you, Monika, for our first presentation in this seminar of Open Vocabulary Learning.
Thank you so much, Camila, for the introduction. Hi, everyone. It's super cool to be here today and to be able to present some of my works. So the topic of my presentation today is towards open world semantic segmentation with no labels, and I'm gonna set the stage by defining quickly what's semantic segmentation and how we're trying to scale it, let's say, to open world, which I guess it's the common topic for all of your seminars. So in semantic segmentation, we have the task is as follows. We have an input image. We have some system, some segmenter that performs a task. And its goal is to produce semantic masks over objects that are on the scene. Typically not only objects, but also backgrounds. So stuff and things like classes. This varies, but in general, we want to assign for each pixel, we want to assign a certain class. And so what has happened before in this classical, let's say, semantic segmentation perspective, typically the scenario is that beforehand, we had to prepare the system to perform this task most likely by supervised training with pixel level annotations. That's one thing. And then the second pillar is that, the system is only prepared for predicting certain set of classes, so predefined classes. And as you can see, there are two main limitations that I see with this approach that basically it's hard to make the system work in open world scenario. So first of all, we have this predefined set of classes that makes the system difficult to adapt to ever-changing classes, adding new classes. Usually, if you want to add a new class, obviously, you then have to go through the whole cycle of annotating the class and then retraining the system. This is a very simplified approach, and I know that there is research that tries to address these limitations. But basically, the predefined set of classes is the main thing we're trying to reduce now. And the second of all, there's this pixel level annotation problem that annotations in general are quite difficult to obtain, and especially for dense tasks such as semantic segmentation. This is a human labor, so these are usually the annotations that are basically costly to obtain. So in open world, or rather open vocabulary, as we are now scenario, we're trying to diminish these problems. And so I like to think about open vocabulary semantic segmentation from a different perspective. So imagine that now it's not the system that is the center of our thinking, but it's rather that we have an image and we have someone, a user, that interacts with a system in order to get a certain answers to his prompt. In this case, it's masks, semantic masks. So now we have a system that is able to understand what users is asking for, and especially which masks to produce, which pixels to predict, and for specific prompts. So in this case, we're expecting the same result as we had before. But imagine now the fact that we're giving some flexibility for prompting, in this case, let's say a user. It gives us certain flexibility, but also poses some challenges. So for instance, instead of bicycle, user could provide a vintage bike, which in this case would also make sense. Also, instead of wall, we could specify what kind of wall it is. So we're moving a bit more into giving this flexibility. We're moving more into referring expressions. But yet, in this case, we're expecting, again, system to be robust enough to understand those prompts and then predict masks that are accurate, and in this case are actually consistent with the previous predictions. So how this is even possible? Is there a magic happening? So I'm gonna just leave this diagram here. You might have seen it before somewhere. So this is the diagram from CLIP original paper. CLIP is definitely the catalyzer of why we're even thinking of semantic segmentation these days in an open world scenario, because all the models or all the approaches that well, my research revolves around are based on CLIP, or in general VLMs, but CLIP was definitely the model that enabled this this area of research. So today I'm going to present just a small piece of reality of open vocabulary semantic segmentation, and also a part of my PhD. With a work CLIP denoiser, teaching CLIP a few dyno tricks for open vocabulary semantic segmentation. And this is work in collaboration with Valeo. So me at Warsaw University of Technology, collaborating with Valeo AI, and all these amazing people, smiley faces here. It wouldn't be possible without them. So as I said, CLIP is at the core of open vocabulary semantic segmentation. And one of the seminal works that sets the stage for all the approaches that we're working currently on is MathClip. MathClip is a work that it's a first work actually that shows that there are certain localization properties within CLIP itself. So CLIP, as you might know, is a method that was trained with is a visual encoder and text encoder, and the visual encoder is trained with text supervision, but only on a global image level. So basically, when you're never looking at patch features, what they actually do, we never supervise them. The supervision is only on a global encoder. What MathClip shows is that it's with a very minimal effort, you can perform semantic segmentation on patch features with no training, just basically taking CLIP as it is. So what they propose is, for ResNet, they propose to just remove a global pooling layer. And for VITs, which will be rather focus of this talk, they show that simply using values of last CLIP layer within CLIP's VIT, and projecting them the same way to multimodal space as we would do with a global encoder, gives us possibility to simply interact with text the same way as we do with normal CLIP inference for image level tasks. And so based on this, you can maybe just to present how the actual forward path with MathClip would look like. So we have an input image that we feed through CLIP image encoder. The CLIP image encoder is completely frozen. And then we have text prompts that we wish to segment on an image. We encode each prompt separately. And on the image side, we're passing CLIP through image through CLIP encoder up until the values from the last layer, as I described. Then we do the projection, which here we call MathClip projection, and we obtain dense CLIP features that same way have the multimodal, the cross-modal capabilities. And the inference, the pixel level inference, is simply for each patch feature that is assigned to a pixel. We simply calculate cosine similarity the same way as we do with CLIP, and by this we can select the class or the text prompt that has the highest similarity with this patch feature. And so it gives us a result, as you can see you can see on the right hand side. Well, the maths are definitely not perfect, but we can see that CLIP already possesses some localization properties. So for instance, Eiffel Tower is in the center, it is located there. Trees, same way, maybe there's some noise between tree and the toy, most likely through color, but we can see that the elements are there. They just need to be refined. And that's exactly what we're doing in CLIP denoiser. So how do we do it? So we propose a very simple modification to the architecture. We're attaching a very small layer, a convolutional layer, literally one layer, on top of CLIP patch features that aims to project the original patch features to the smaller representation space that aims to reproduce or to refine the correlations of those features within an image. So here, if you look at the visualization of the patch features, if we put a point on a certain patch feature, like in this case, it's on Eiffel Tower, you see that the correlations within Eiffel Tower, so they do represent and they do follow the boundaries of an object, and that's exactly what we're utilizing in our approach. So we're using this sort of affinities, correlations between features within an image to refine the final outputs of segmentation. And how this guided pooling looks like. So the affinity map is an input to guided pooling. So this refinement, a guided pooling, is a simple aggregation of clip patch features, but within the correlations predicted with our trained layer. So here in this case, you can see we put a point on a cat, and then we'll be refining this patch feature within cat by aggregating its neighbors within a cat. So literally weighted pooling of this feature. A very simple solution that leads us to something that it's, well, refined with respect to mask clip that represents we have coherent masks that follow objects boundaries. So now you may ask, where's Dino and where is this module, the convolutional layer coming from? So that's where actually Dino comes into play. The motivation for this whole work was that we have clip that has amazing zero-shot capabilities for image-text interaction, but it lacks localization properties as we saw. But on the other hand, we have a bunch of great models, self-supervised learned models that have the actual opposite. So they do have this complementary abilities for localizing objects within patch features that Clip doesn't possess. So that's what we're utilizing in this work. How do we actually use Dino to teach Clip to reproduce correlations? We have an input image, and we feed the same image to Dino and to Clip image encoder. Then for Dino, we create the same affinity matrix as I showed before. The affinity matrix is again correlations of the features from Dino, so it's also last layer of Dino model. And as you can see on this example below, Dino affinity matrix is much cleaner. It possesses all the knowledge of where the objects are located and their consistency. So we can clearly cut, for instance, a mask just based on the correlations, but we cannot name what the objects are, right? So we are using this affinity matrix to supervise our convolutional layer in order to reproduce the same space as Dino would, let's say, present. For this purpose, we use just binary cross entropy. So technically, we're setting a threshold where which patches should correlate with each other. So then it's matrix of 0, 1, and then basically that's our supervision to then train our convolutional layer. The whole training is quite efficient. So what we do, we use only 1,000 images from ImageNet, randomly sampled, and also the whole training, since it's a very small layer, the training takes only about 6,000 iterations of patch size of 16. So basically, you can fit it on your one GPU, and you can train it within 2 hours, and the result is quite nice. So let me talk about the result now. I won't be presenting any numbers. I think what I like, the coolest part of all open vocabulary methods is the actual open vocabulary interaction. Obviously, we did evaluate our model on standard benchmarks. The work was accepted at ECCV, so there is a certain amount of things that you need to definitely show that method performs at certain level. But for me, the coolest part is the actual random images and prompting them. So here we have an example of a portrait of Ada Lovelace, and we prompted it with different prompts that could be difficult or could be noisy. And so for instance, for Matclip, we see that the prompts, the segmentation masks are noisy. And Clip Denoiser nicely refines them, except for one thing. There is this hairdo of Princess Leia that kind of stayed, which we found actually funny. And we could say that even it's a failure case of our work, yet still decided to make a fun of it. We also observed that that method works pretty well on maybe the specific domain images. So in this case, we have an image. We have a painting of Edgar Degas, and one of my favorite ones. And we see that Clip Denoiser can also perform well on such difficult and challenging images where Maskclip produces very, very noisy results. We also have some more sophisticated prompting. So in this case, we have two dogs. One is big and one is small. And in this case, Denoiser also refines masks pretty nicely. But also you can see that within Clip itself, this sort of understanding exists already. And finally, we have also some personalities from pop culture. These are the concepts that again exist in Clip, so we can see for comparison, you see that Maskclip already possesses those localization abilities where a particular concept is located, but Clip Denoiser nicely refines them to produce better masks. And just to conclude Clip Denoiser's qualitative results, here is a video of my dog not far from my parents' house. As you can see, well, Clip Denoiser is not meant for video segmentation, but if you run it frame by frame, there's still some consistency with no specific temporal supervision, and it looks pretty nicely also with respect to what Maskclip does. So just to conclude, so I presented one method for open vocabulary semantic segmentation that is definitely just a very small step towards what I would describe open world semantic segmentation, and there's definitely a large room for improvement. But I think the interesting conclusion, and I'm seeing it in general in recent weeks, in last week's it's happening, is that the combination of those two representation learning paradigms, so we have Clip and SSL on the other hand, can yield powerful models for pixel level tasks, but not only. And just simply combining them and marrying them feels like an exciting avenue for research. And we're already seeing fruits of this idea. So we have efforts from the team at NYU. They do great work on exploiting the complementarity of both visual encoders for VQA, for instance, and old generative VLMs. There are also new works from Dino team. There's Dino with Dino TXT aligned with text. There's also tips from Google and Flick from Google. So there are new encoders that do combine both paradigms, and I think that's great. And they show a great results. And with this, I think I leave you with this, and I'll be happy to take any questions.
Wonderful. Thank you so much, Monika, for that great presentation and amazing work.
Thank you.
This is an informal seminar, so if you guys would like to unmute yourselves and ask questions, just raise your hand and do that. If there is no question yet, then I would like to start. I have a question. I have a few actually. So when you trained basically the Dino with the Clip image encoder with binary cross entropy, so you said that you select randomly 1,000 images from ImageNet, but the whole thing takes 6K iterations and it's choose a few hours. So why do you pick this random subset of images?
I think the goal was to show that, well, first of all, we didn't want to, the whole projection layer is very simple to train. There is not a lot of parameters to train in the first place. So the idea here was to show basically the starting point was using Dino as it is without even this projection layer, and it works the same. So that was our starting point. The thing is that when you have two BITs to run, this adds up a significant compute. So our idea was to, okay, let's try to just distill some knowledge from Dino just to this small layer. By this, you have a forward pass, and you have a segmentation that it's the model that it's fast and efficient within a single forward pass. So the goal for this layer was, well, let's just to distill the localization properties from Dino, but there was, we know that it's just a simple thing to do because we have two frozen encoders. So the idea with the 1000 images was to simply show that it only takes 1000 images. So that's why we were randomly sampling, because it actually doesn't really matter what kind of images these are. I think in the paper we're doing like I think average of like 5 random samplings of those 1000 images. We also trained on another data set, and we just basically showed that giving more data does not improve the performance. Where with this layer and just with 1000 samples, we're reaching the performance of if we just use the Dino off the shelf with no just the original features as they are. So that was the whole idea for those 1000 samples. We actually believed it could take even less due to deadlines, and that was where we set the foot at. But we actually think it could be even less.
No, I mean, if it takes 2 hours, right? I mean, that's already great.
Yes.
That's that makes a lot of sense. Any questions from anybody else?
Hello, I have a question. Actually, I have 2 questions. The first question is that if I understand correctly, the core idea of clip denoiser is that you would like to use the good geometry aware and capability of Dino to get the feature pooling of clip,
Yes,
and
exactly.
take advantage of the semantic awareness of clip and combining the two to reach the final
Yes.
result. And
Exactly.
have you ever thought about using SAM to get the clip? Because if you resize the masks yielded by SAM to the feature map dimensions of clip, you can actually use the SAM masks in the feature map dimension to crop clip features, right? And I'm not sure that you think like the Dino guidance and SAM guidance, which one would be like actually better, because they are both self-supervised, and I think the quality of the mask itself should the SAM will have the better result. So this is my first question, and the second question is that, and if we use the method, that is it possible to scale it with more data?
That's these both are very good questions. So for some, the work dates some one. I mean, when we were working on it, it was rather the first version of some that was around that time was out, because the paper we put on archive quite a long time ago. And here the idea was that yes, some masks we could definitely use them, go like fix the resolution and use mask and improve within some masks. Here with the prompting, I'm not sure how it would work, because I know that some does require prompting, requires prompts. So I don't like in if you think of denoiser, it's just we're just trying to fix the features or like improve the localization properties. With some, it's really like segmentation oriented, in a sense that you need to prompt a specific pixel that you want to, or with a text, from what I understand. But by the time the text prompting in some wasn't that efficient.
But actually, you see, like your clip, the noise clip masks you have, right? Actually, they can serve as a natural prompt for
True.
the SAM,
Okay. Right? I give it back to you. With the problem with that, with mask clip, or with clip rather, that there is like a lot of very noisy features. It's not even that the masks are inaccurate, but there was plenty of noisy features that were sort of outliers. and it was actually very difficult to set a boundary whether is it a small
Yes.
object or is it actually a noise. So with this, in this case, we would need to definitely pre-filter them somehow in order to fit them to sum. So that was maybe it wasn't really obvious how to do it. That's one point. Then, well, I was working with a team that was very, I mean, overall, we're really interested in like purely unsupervised or like self-supervised approaches. Obviously, Clip is categorized to, let's say, weakly supervised, but the least supervision, the better. And so SAM is, at least in the version 1, is trained with full supervision with lots of annotations. So for us, it wasn't very exciting to use SAM as it was. I know that it maybe everyone uses SAM nowadays as it's given, but it's a highly supervised method. So the whole story of like, yes, reducing annotations, that wouldn't be the case because we would use actually pixel level annotations. And Clip denoiser, like if you look at the whole pipeline, what it took from Clip, training Clip through Dino, through our training, there were no pixel level annotations at any point. And I think that's what was the most compelling to us. And that's what led us our research basically. So that's on SAM. And the second part was if you, the question was if we would put more data if it scaled better.
Yes,
That
yes.
was
I
your
mean,
question, right?
yes, I got the point that you want fewer data to yield to the results, but in really like in the applications, many users might, if we have data, I just want to scale it to make it works better and better on my task. And so given your method, is there a way that if we have data, we can simply scale it with 10K images or even 1 million images?
That's a good question. So I think for this particular setup that we had with open vocabulary segmentation and this particular Clip and this particular Dino, adding more data wouldn't help. I think we actually reached a plateau, at least for the benchmarks that we were considering, that Clip started to be a limitation. So if you saw our comparisons, mass Clip versus Clip denoiser, there is always, you see that we're never actually getting out of Clip's limitation space. So if, for instance, in the case of classical benchmarks, if we saw that the label just wasn't right, we couldn't improve the label without actually, changing prompting or working with text. So adding more data just to fix the Dino layer, our trained module, it wouldn't help. I think we reached really the plateau, and Clip was the bottleneck. I think the next step in order to push the numbers in that case would be working with text prompting or actually working on Clip parts rather than Dino part. I think the refinement part was actually not bad. I mean, obviously you can see that the boundaries could be improved, but this is not the data. I think this is rather just post-processing tricks, like pixel, going back to pixels and refining with respect to boundaries, like post-processing, like CRF, for instance, things like this, but it doesn't require data. So to sum up, I think with Clip denoiser the way it was with one layer, more data wouldn't help. Even adding more layers wasn't really helping in this case. I think for us at that point was the Clip itself was a bottleneck.
Thank you for sharing the experience. I appreciate that.
No, I'm happy to.
Okay, if there are no more questions, thank you, Monika, again for that great presentation.
Thanks for having me.
Of course. Yeah, we would move on to the second part of this seminar. Miu will be presenting. Miu is a third-year PhD student in deep learning and computer vision at the University of Trento in Italy. He is currently a visiting graduate student at the TOE Lab and UCLA on scene discovery and understanding for digital causing creation. His research focuses on open world perception and understanding through visual inputs, with a keen interest in multimodal learning and novel knowledge discovery and reasoning. Recently, he has been exploring how LLMs can enhance vision tasks in real-world, open-world settings. So I hand the mic over to you, Miu.
Okay, thank you, Camila. Okay, can you see my screen?
Yes, we can see your screen.
Okay, cool. Okay, so hello everybody. I'm Michelle Liu. You can call me Miu. And today I'm going to presenting an exploration about novel vocabulary visual recognition using natural language. And so now, if we want to recognize like a common object, we actually do not need to know a predefined vocabulary. We can simply send like a image to some foundation models, and usually it can give us pretty good result and high accuracy, and no predefined vocabulary needed. But let's imagine one case, like if we are like a young boy, we have no knowledge about bird species, and we collect several unlabeled images from Amazon jungle, and we have no idea what are the potential or possible bird species in this region. Without knowing such a vocabulary, how can we use a VRM or multimodal ARM to help me to recognize this bird species? And we did some explorations. When we send this kind of foreground images to these foundation models, and usually the results are pretty bad. This is because these foundation models does not have a clear guidance to focus on the foreground details in the image to help them to distinguish one foreground category from the others. And this is pretty much a inherent challenge about foreground visual recognition, which is called the intro-class similarity. But if we know a vocabulary, the possible names, actually we can simply use clip to conduct such a foreground visual recognition and yield pretty good results, as we can see in many papers. But there's one question that we are no expert in the foreground domain. Usually, it's very hard to know the possible category names for foreground data. Taking the contact bird as an example, there are 200 foreground bird species. If we are no expert, it's really hard to define such a vocabulary to help us to conduct such visualization about an unlabeled data set. So with this in mind, we are thinking about, can we actually build an effective system that can automatically discover the foreground concepts from few unlabeled observations and then thereby class them without using a vocabulary. So we did this exploration in the work from last year. First, we defined this is actually a vocabulary-free foreground visual recognition task. We would like to discover those vocabulary from unlabeled data and then use this vocabulary to conduct the subsequent recognition process. Through this, we would like to build a system that is just like a human do. So as a human, usually when we say like a bird, if we want to know the bird species, we would like to consult some expert, and the expert usually will ask that, can you describe the bird that you see to me so that I can help you to reason over it? And and then we describe it about the wings, the color of the wings, and the length of the beak, and the bird expert can usually tell us what would be the possible bird species based on our description. So that based on this human inspiration, we use a VQA model and a LLM to build a system to mimic this human consulting process. So this is the overview of our framework. So we can go through it step by step. So first, leaving still unlabeled images here, we have no prior knowledge about these images. So we can first actually use the VQA model to identify a supercategory from the image, from these few observations. For example, like a bird, if we have some bird images. After we obtain these supercategories, and we can use this supercategory name to query LLM to obtain a list of useful visual attributes that can help us to distinguish a specific foreground bird species. And after we obtain this list of attributes, we can then send this attribute, wrap it up as a question, and to query a V2A model to describe these attributes one by one, to obtain the attribute value, which is actually a description for each of these attributes. And after we At this stage, we can actually from a few unlabeled images, we can actually obtain a super data rename and a list of attributes and the description for each attribute which are grounded to our few observations. So now we can actually wrap up everything into one prompt and taking advantage of the reasoning capability and the word knowledge of an LLM to help us reason the possible category names from our few unlabeled observations. This is actually we are consulting a human expert that to ask the expert that what are the bird species from our observations. And now we have actually the freshly reasoned category names, and they are pretty much noisy. And because IRM can hallucinate, sometimes it gives us incorrect answers. But since we have few unlabeled observations, so actually we can conduct a very tiny refinement process using clip a VRM to ground and filter out those noisy image names that are irrelevant to our few unlabeled observations, and then we can obtain a refined category names. And then after we obtain these refined category names, which is in natural language, we can wrap up it with our few unlabeled observations to construct a multi-model classifier, which is actually the average of the embedding across two modalities. And after we obtain this multi-model classifier, we can simply use clip to conduct a fine-grained visual recognition pipeline on a large scale without actually knowing the vocabulary. For example, we can actually install this classifier into a smart camera in the Amazon jungle to monitor and recognize the bird species that potentially living in this region. And so this is a actual overview of the prompt and the working process of the whole system. As we can see here, we obtain the categories and then we obtain the descriptions, and then we wrap everything up into one IRM prompt to reason the fine-grained category name. So no further training required, only forward inference, and we can conduct such vocabulary-free recognition process. And so there are some experiment results. Since our task is actually open-ended because the reason category name might not 100% the same as the ground truth. So we use two metrics to evaluate our system, the semantic similarity and a clustering accuracy. So as we can see here, given 3 images per class as the field observation, our method is able to yield a quite satisfactory results across that 5 fine-grained benchmarks like bird, car, and also flower and pets. And what is worth to notice that, and this kind of reasoning method can actually outperform some name retrieval-based prior arts. For example, these two methods usually build a large name database by using WordNet or even more millions of caption data as name candidates, and then use clip to retrieve the name they want from this database. Later on, we will show that the disadvantage of this kind of retrieval-based method. And further than that, we are very curious about how this system will perform compared to humans. So we conducted a human study. We actually sent out the questionnaires to some layperson, and that is no expert in car or in pet, and we compare human recognition. We let the human to discover the names from the unlabeled data, and then we compare the results with human discovery and our system. And as we can see that for Stanford card, actually most of the layperson since actually outperform most of the prior method, because even if we may not like car very much, but we actually see a lot of cars every day and hear about it a lot. So actually we observed this, and other than that, our system actually reached a very similar capability of a common layperson, although being far behind the human expert. But for PAD, we observed that most of the methods can actually outperform a layperson, and this is very interesting because even if we see a lot of PADs, but actually in real life, we if we are not like pretty much let's say a big cat or dog lover, we actually do not know a lot of very fine-grained pattern names. So this will result in this poor layperson performance, and this is very interesting. And there are some qualitative results, as we can see here. Our system is attribute based, so there are one failure case that is very interesting. So the ground truth for this image is actually blackberry lily, and our system actually wrongly predicted the name as orange spotted lily. But if we think about this and observe and try to have a look at this image, and it is a wrong answer, but actually it's not that wrong, because actually since we are attribute based system, the LLM actually told us a fabricated name based on the description. And if we think about this means that the system is actually to make a better mistake by using these attributes. And this observation is actually more significant if we do a reverse comparison. So we use the reason and classified name of our system to generate the images by using Stable Diffusion and using Google Image Search API. So when we try to search the blackberry lily with our wrongly recognized name orange spot lily and compare the generated images with respect to those generated with ground truth, we can observe that the image generated by our wrongly written name are actually very similar to the ground truth, because we took the attributes into consideration. And lastly, for curiosity, we also explore a little bit this time system on virtual objects like Pokemon. And so this is very simple. Maybe it looks a little bit dummy, but actually it's very challenging if we think about it. It's not only fine-grained, but it's also made the model can be easily confused with its real-world analogs. For example, and when we try to reason the name of Squirtle, we observe that many of the name retrieval-based methods using CLIP, they retrieve the turtle for Squirtle. This makes sense, right? Because Squirtle, the real world analog is a turtle. Because for the retrieval-based method, there is no guidance that to ground the retrieval process into the scope of Pokemon. But we can see that our reasoning-based system, since we reason it step by step, we recognize as a Pokemon, and then we try to distinguish a fine-grained categories from among all the Pokemon. So our method can actually give a better result without being confused by its real-world analogs. For example, like turtle or pita or bird or something. As we can see here, other retrieval-based method usually it only performs good on some really common famous Pokemon like Pikachu and Bulbasaur. This is an effect of a CLIP training process. It's related to CLIP training data. Yeah. Yes, and that's it. So now we can actually have a system to automatically categorize fine-grained images without actually knowing the vocabulary. And however, actually in real world images, if you think about it, not all images are object centric. For example, like this. So this no guarantee that each image contains a primary object, right? And if we want to organize this image, how can we do that? How can we do that? Because we can actually organize this image based on many dimensions. For example, object category, or sorry, my laptop is starting. Yeah. Or action or time of day or mood is actually a pretty much open-ended task. It's starting again. Yeah. So there are some prior works trying to explore this unstructured image collection task, and the core idea of prior was that since we can organize the image based on many criteria, grouping criteria. So they let the users to specify a criteria, and then they try to automatically group these images based on the user specified criteria. But if you think about this, as a user, do we really know how to specify or predefine such a grouping criteria if we have 1 million unlabeled images? I mean, we are trying to understand our data, and then if the system asks us to predefine a criteria, that is pretty much challenging for us, right? And so this is actually a cheating and add problem. We don't know the data. How can we specify such a vocabulary? And the second limitation is limitation is that if we let the user to specify such criteria, sometimes the data can tell us more. There are some like novel insights or novel criteria about the images that may be ignored if we always use our limited knowledge to specify such a criteria. So our idea is that why not to let the data speak for itself, which is to say we want to build a automatic tool that can uncover diverse semantic substructures given given a unlabeled data set without any prior knowledges. So in our recent work, we explored this direction to organize the unstructured image collection using natural language. So first, let's define the task. So we actually we first touch on open-ended semantic multiple clustering. So given an unstructured image collection, we would like to first discover multiple grouping criteria automatically from the data, and then subsequently organize the data under each criteria into semantically meaningful clusters, just like that. And then this is actually very interesting. We observed that once we try to discover this criteria automatically from the data, we can actually reveal and uncover some novel insights from the data. So the core design, the design core of such an open SMC system is that to discover this grouping criteria, it requires us to reason over the entire data set concurrently to find this grouping criteria, because to group images, we cannot only look at 2 images, we need to look at the whole. So there's no vision system can encode the millions of images concurrently to allow us effectively reason over it. So to this end, we propose a two-stage method called X cluster. How we do that? The core idea is that we want to use text descriptions as a proxy to reason over the images, and we propose it's for actually 3 variants of the system. So we can given an image data, like millions of images, we can actually snitch them into small batches and send it to like a MLM, like Lava or something, to propose this kind of criteria. We can also convert each image into a small tag, and using these tags as a proxy, wrap everything up into one prompt to the LLM to reason the criteria. We can also convert image to captions to do the same. And after we obtain the criteria like in a pool, we can actually, and then we can conduct the corresponding grouping process for each criteria. And the same as the criteria proposer, we explore 3 variants of the semantic grouper. We use text, caption, and the victory model to condition the grouping process based on the discovered criteria to group the images along each dimensions that is defined by the criteria. So we also propose 2 data sets to evaluate our system. And so first of all, we would like to check how well the system can predict such grouping criteria. So we observe that across all the proposed variants, the caption-based proposer and can actually achieve a very good recall. That is the true positive rate among all the annotated criteria. Yeah, and so as we can see that it can actually hit most of the annotated criteria in the unlabeled images. And then we would like to study which semantic grouper works better, the caption-based one or the tag-based one or the image-based one. So we evaluate the semantic accuracy and translation accuracy across each criteria on each benchmark. And and then using the harmonic mean of the cluster accuracy and the semantic accuracy as a metric to decide which one is the best. And we will observe that the caption-based one actually ranked first 12 out of 19 tested criteria based on the harmonic mean of the two metrics. And here are some qualitative results of the systems. This is the grouping result of the system automatically. We didn't define anything, and all the class names and criteria are automatically discovered by the system. Yeah, these are some qualitative results. And lastly, I would like to show some interesting applications, and I can jump into here a little bit. So I jump to the second one directly. So now we use our system to try to discover the potential bias of text to image generated model. One moment. Oh, yeah. So how we first actually selected 9 occupations that usually is linked to some stereotype. And then we use a portrait photo of a occupation to generate 100 images for each occupation by using Stable Diffusion H large and also DALL-E E3 respectively. So we want to see that can our system to find a potential bias from the system. Yeah, not surprisingly, we found that our system can discover the criteria to group such image based on gender and race or something else. These are actually well-known social bias associated with certain occupations. As we can see that on these well-known biases, DALL-E is actually pretty good. It's doing pretty good because DALL-E has a guardian system, but Stable Diffusion actually present a nearly total bias about gender and race. And you can see here, I mean, all the factors are met, and this is pretty bad. And but these are, we all know this potential bias issue about this text to image generation models, right? This is not very surprised. How about that? Our system discovered a lot of novel biases beyond the well-known ones. For example, the hairstyle, the skin tone, and also grooming. For instance, we found that the image generated by DALL-E about teacher, and the 80% of them actually are clean, have a clean shaven. And then we observe like CEO is not only, we observe that the generated image from Stable Diffusion and DALL-E like present a hair color bias. For example, the Stable Diffusion, the generate images say about CEO always have a gray hair and a little bit old, and the DALL-E generate image always have a dark hair. So these are actually novel biases that we can use our system to discover from the unlabeled generated images. Next, we would like to use our system to run on social media images to analyze what visual property actually makes an image popular on social media. And so we conducted a study on some social media images from Flickr, and we ran our system to discover 10 grouping criteria. And then we select the cluster that has the most average popularity, but maybe few data points. And then we also select the cluster that has the major data points yielded by our system. As we can see here, we observed a very interesting effect. We observed that the most popular cluster and the major cluster usually has a sharp semantic contrast. For example, based on activity, the popular one usually is about musical activities, but the major ones are usually rest and relaxation. And for color themes, actually dramatic color attracts more attention, but most of the picture uploaded on the social media platform are about like are having a natural color. And beyond that, surprisingly, we actually found some non-safe to work content from this data set that it has never been discussed before. For example, based on color themes, we found that in the dramatic color cluster, the most popular images, the top popular images are actually contain some violent or even bloody visual content that actually attracts the attentions. That's why they observe the popularity. And we also found the top popular images in the from the cluster of young idols under age group that contain a little bit like sexual contents. Yeah. So this suggests that many of the time the social media image gain the popularity is actually due to negative or provocative visuals that attract people's attention to gain popularity. So yeah, this is my presentation about today. And so the conclusion that open vocabulary is cool, that we observe that many of the time it's really hard for user to know or define such a vocabulary prior to their applications. And also, if we always use a predefined vocabulary, many of the time we might ignore those novel insights that may present in the data. So by using natural language as an intermediate proxy, actually we can develop many interesting systems to automatically discover such vocabularies or semantics from unlabeled data to let the data tell us for themselves. And lastly, I would like to thank my co-author collaborators about their prior works. And yes, without them, I cannot make it. And thank you for listening and time.
Wow, that was an amazing presentation. So much work that you managed to present in that short amount of time.
Yes, I'm sorry, too many contents.
Yes. Okay, so then I open the floor for questions. If anybody has a question, feel free to unmute yourself and ask.
Hey, Mew. Good to see you. I have a question. So on the recent work that you proposed or like demonstrated, you said that the captioning model was performing the best for this exploratory clustering. Were you using captions from the existing data sets, right? Like I saw you had Coco there. I was wondering if you were using those captions or if you were only using like captions generated from LLMs, and if you were using LLMs, what kind of prompts were you testing?
Yeah, actually, we only use the caption from the generated LLM. So for the first stage, we only use one prompt, describe the image in general. That's it. And because we want a overall understanding and description about the image, and so we can send this general description to the LLM to reason over what are the potential grouping criteria, because we do at this stage we only want to ground the reasoning process of our whole data set, right? But for the second stage, we actually use the automatic generated prompting. So given a criteria like an action, we send it to a LLM to automatically generate a prompt for the caption model to describe this image, describe the action of this image. So we can actually have a criteria specific caption for each image that allow us to label it later on to conduct the clustering process.
Okay, so you were providing kind of a list of these different groups. So like describe the activity in these images. Okay, so
yeah.
Okay, I see.
These groups are actually discovered from the first stage. The first stage, we discover these groups, the criteria like in a pool. And the second stage, we just take each of the criteria from the pool and describe it based on this criteria one by one for each image. And then we aggregate everything together to use the LLM to label it and to label the caption actually, so that we can actually also label the image. And then we group them together based on the labels assigned by the model. And so we obtain a substructure of the data and for this criteria. And then we go through each criteria one by one. We can obtain different organizations of the same data.
Okay. And I guess a follow-up question. So you had this chart where you were measuring performance, right? And like performance in the upper right corner was better, right? And your captioner method was up there. What were you measuring? Were you using clustering metrics for this? Or like what was
Yeah, it's too fast. Yeah, sorry.
No, that's okay.
So there are two dimensions. we use to measure this model. The first one is semantic similarity, and the second one is clustering accuracy. So the clustering accuracy can tell us how consistent the predicted substructure structurally similar to the ground truth ones, the organizing. And the semantic similarity can tell us how similar semantically of the predicted names that are similar to the ground truth. And by using the two, we measure the harmonic mean of the semantic accuracy and also the cluster accuracy to decide which model is the best. So when the model can yield a best harmonic mean, it means it gives semantically and structurally similar substructure prediction results with respect to the ground truth.
Okay. Yeah, very cool work. Thanks.
Yeah, thank you.
I also had a question similar to Tyler's regarding the evaluation of the clustering. So when you do this clustering and you extract basically what concept all of these images have in common, which I thought was super interesting, like how do you evaluate that? How do you evaluate whether, say, has something related to music, everything in that cluster?
Yes, so we have the annotation. First of all, for our data for the benchmark we use, we have actually annotations for each of the criteria, like music or action for the same data. The images are the same, but each image has multiple annotations on each criteria, and then we evaluate as we described before, the semantic similarity between the prediction and the annotation. Because for example, like activity, we might say dancing, we might also say popping or hip breaking. They are all dancing, but the ground truth might be dancing, but our predicted result might be breaking, or ballet, or popping, some other names about dancing. And they are very similar, but they are not exactly the same. So we actually encode these two names into sentence BERT, and then we can obtain the embedding of the ground truth and also the embedding of the predicted names. And then we measure this total similarity between the two embeddings. And this is a soft measure because we cannot guarantee that the predicted name is 100% same as the ground truth. Because the ground truth is actually, if we think about it, the ground truth annotation is actually biased to the annotator's understanding about a certain concept, right? Because we can actually have multiple names for the certain concept. So we chose this kind of soft measure to measure how similar the prediction is with respect to the ground truth.
Okay, yeah, that makes a lot of sense. Yeah.
Yeah.
Okay, we are actually over time. So unless there are any more pressing questions, I would say that we end this month's seminar now. Thank you again, Miu and Monika, for those great presentations and for everybody who joined.
Yeah.
Uh,
Okay, so thank you, everybody. Happy to see you again, Tyler.
And have a great day, everybody.
Thank you. Bye-bye.
Bye.